So I'm Berro, and now I'm an assistant professor in molecular biophysics and biochemistry at Yale. But actually, I started as a mathematician, applied mathematician, on mathematical modeling. And when I was in graduate school, I was only doing mathematical modeling in close collaboration with our experimentalist friends. But I realized very quickly that there were so many misunderstandings that I decided that for a postdoc I would go to an experimental lab and do experiments, right? And I never came back, basically. That's not completely true. But today I'm going to talk about a couple examples of where my initial training in mathematics and a little bit of physics can be very useful for understanding even long-studied systems. And as someone said yesterday, sometimes the lowest hanging fruits are really at the interface of disciplines, right? Since we're Sunday morning, it's 9 o'clock, we're going to start with a quick warm-up question. It's, how do you model a cow, right? We usually say, let us consider a spherical cow, right? So I have 4 questions. How far can we catapult a cow, right? How long does it take to freeze a cow in liquid nitrogen? How long does it take for a cow to digest grass? And how does a cow run, right? My point here is, for each of these questions, how would you model the cow? Right? First question, how far can you catapult a cow? From your first year freshman physics course, you know that maybe just a point with a mass is sufficient to give you a very first good approximation of how far you can send a cow. Now, if you want to include friction, maybe the spherical cow is a very good approximation, right? Same idea with how long does it take to freeze a cow in liquid nitrogen, if you ever want to freeze a cow in liquid nitrogen. It doesn't really matter. I mean, you know, the tail is going to freeze very quickly, probably. The legs are going to freeze very quickly. Ears also, and the head. And so what really matters is maybe the entire body. And, you know, having a spherical cow here is also probably a very good first approximation, and what really matters in this system, in this question, is the surface to volume ratio, right? Now, if you want to know how long it takes for a cow to digest grass, the cow, physically speaking, doesn't really matter so much, right? So you're going to have a 0D model, it's completely fine, and it's going to be a black box with an input grass and an output milk and gas and other stuff. And we've probably can even have phenomenological function, transfer function here, and maybe you want more details depending on the question, more precisely the question you want to address. Right? And the final question, how does a cow run? Well, now you maybe want to focus on how the legs work, and a sort of system of spring dashpot model would be probably the most appropriate, right? And so the point I want to make here with this slide is that what drives the model is the biological question, not the other way around, and also what kind of data are available for you to build a model and then test the model, right? So after this warm-up, I'm going to talk about some of my research a little bit. So my lab is interested in how molecular machineries generate forces in the cell. And we work more specifically on collagen-mediated endocytosis. For very basic description, you have a flat membrane at the beginning, and you want to make a vesicle at the end, right? So you see there is quite a lot of topological changes on the membrane that happens. In the molecular mechanisms for this to happen is fairly well conserved in eukaryotes. And what's been shown in the last 10, 15 years is that actin is important for this process to happen when membrane tension is high, right? Now the question is, what is its role? We know it's there, we know it's important, but we have no idea how it works and what is its role. And so is it to produce forces to elongate the pit here? Is it for the scission of the vesicle? Or is it just to reduce membrane tension around? Okay, so I'm not going to answer these questions today because we're still working on that in the lab. I'm sorry. But I'm going to present two other questions that are working towards this direction. One is, what are the molecular mechanisms for actin dynamics? Because we know it's there, but we don't know exactly how it works. And the second question, if I have time, it might be a bit short on time, but if I have enough time, I talk about some more organization of the filaments during the phases. Right. So the challenge in studying calculated endocytosis is it's very small. So the scale factor is 15 nanometer, the vesicle is about 15 nanometer diameter. The molecular machinery around it is about 200 to 300 nanometer diameter. And the other thing is, all these deformations happen very fast in less than 10 seconds, right? So the challenge here is if you use the traditional microscopy methods, you can get some information, but you don't go very far. So the fact that it's small makes it diffraction needed in fluorescence microscopy. So the best you can expect from traditional fluorescence microscopy is a blurry spot like that. So to overcome that, you can try to use electron microscopy so you can get the shape of the membrane, but the problem with electron microscopy is you don't know where the proteins are. And in this particular example, with where actin is present, it's actually almost impossible to see the details of the actin organization here. It's for technical reasons. And localizing proteins is there are some methods, but they're not quantitative and not very precise, right? Now, for the other problem with electron microscopy is you lose all the dynamics. You have to freeze the samples or to fix the samples, and you lose all the dynamic information, which you can get from a fluorescence image, right? So one strategy we use is, can we get more information out of these fluorescence images? And the idea is to turn the fluorescence signal into a number of molecules. So we work with yeast, and the nice thing with yeast is you can edit the genome very easily. And the idea here is if you edit the genome to have the sequence coding for a green fluorescent protein, just at the end or at the beginning of your gene of interest, then now every time the cell produces your protein of interest, it attaches a fluorescent protein on it, right? So there is a one-to-one relationship between the number of GFPs you can have in the cell and the number of proteins. So now, getting the number of GFPs could be feasible if you look at the fluorescence signal. If you know how many GFPs you have, you know how many proteins you have. So to get that, you need to calibrate your microscope to turn the fluorescence intensity into a number of molecules. So for that, we have we built a calibration curve where we have 7 strains, yeast strains that express proteins with a GFP attached to it. On one hand, we estimate the average concentration in the cell through different methods. So we use quantitative immunoblocks, but you could use quantitative mass spectrometry and other methods. And so that's going to give you image the cells on your microscope, and you circle the cells, you get the entire fluorescence, and you get the point on the y-axis. So then you do a regression, and the slope of these curves gives you how many fluorescence units do you get per one GFP molecule, right? So now you can apply that to your movies. So you track, so every single dot here is one endocytic event, and you see it comes and goes. You can track one single one, so here I go into the membrane, just for reference. You extract the fluorescence out of this movie, and you can make a graph number of molecules versus time for the protein of interest. Right here is fibrin, it's a crossing curve of the actin filaments. So you don't get such a nice signal right away. You need to collect a lot of data. We developed a new method to align the data more precisely than before, and you get something very smooth and very nice. All right, so now we're going to apply that to really the system of endocytosis, and more precisely about, as I told you earlier, the actin dynamics, right? So here what we did is tag 4 different proteins that are involved in the mutation of actin filaments. So this protein WASP that comes early, that includes the alpha-3 complex here, and starts actin polymerization. There's a gapping protein that prevents growth. But what I want you to point out here is you assemble about 8,000 actin subunits, about 300 alpha-3 complex, about 200 gapping proteins, right? And so the thing here is, it's kind of boring in some extent, because it's what you would expect from all the knowledge that people had at that time on cell motility. It's exactly the same mechanisms, molecular class for cell motility. A lot of in vitro work has been done to characterize interactions between these proteins. A lot of rate constants have been proposed. And so, sort of boring to begin with a project is, well, can all the data and all the parameters we know, can that explain this fast dynamics of actin assembly and disassembly? Right? Fairly simple. So for that, again, that's the pathway of activation of the alpha-3 complex by WASP that binds to the side of the filament, and the filament can grow a new branch, and you have ATP actin that comes at the part end here. The ATP is hydrolyzed, PI is released. On ADP actin, this protein called ADF-partin can bind and separate the filaments. And actin subunits can be disassembled from this end. And you have the capping protein that blocks the polymerization. Right. So as I said, fairly simple system. We didn't have any information, clear information about the organization of the filaments. So what we decided is to do a non-spatial model. So basically, like the cow is a black box with input and output. And it turns into a system of ordinary differential equations, that we may go into the details, with pretty much no free parameter. There was only one free parameter. Still kind of boring. So let's just simulate it. It should work, right? The problem is it doesn't work. I think you can see the model, which is the plane lines here, don't fit with the experimental data, the symbols. The first very striking thing for actin until here is that it can sort of assemble fast, but disassembly is terrible, right? So doing the mathematical model, you can say, well, there's something wrong. Let's tweak some parameters and cheat a little bit to work. Or if you're a bit informed, you say, let's make a prediction and make everything disassemble faster. And so the prediction we made is not only if coffin severs the filaments, but also it releases chunks of the meshwork in the bottom. And if you do that, you can actually disassemble much faster. So that's the first prediction. Second prediction of the model is that you see there is quite a delay between the experimental data and actin assembly. And again, you can tweak any parameter, but when you go into the literature and you dig into the details, you realize that some of the parameters are less well measured than others, and there are good reasons to think that this parameter here and here can be wrong in this system, and can be different, sorry, in this system. So that's the second prediction, and not just a tweak, that are totally complex as a faster dynamics in this system. Right? You can make, so if you do that and you change the parameters, everything fits well. It fits. Now you can make also with the model, you can make more predictions, but stuff that are very hard to measure, like the number of ends that are growing at the same time. And so we show that actually a very small number of filaments are growing at the same time. And the average length of the filaments is fairly, it's about 100 to 150 nanometer and remains roughly constant. Okay, so these tweaks, you know, I keep saying that they are predictions. The prediction is really a prediction until you really test it and you prove it, right? And so that's what some of my colleagues did, and all these 4 predictions have been shown to be right or relatively right? So if you use, develop coffin mutants that don't sever the filaments so well, you realize that the disassembly is much slower, whereas the initial phase doesn't change so much. If you purify actin from this particular yeast and the artificial complex from this particular yeast, and you do the in vitro experiment, you can show that the artificial complex has a better activity. There are also other proteins that increase the activity of the artificial complex. And for the number of filaments, short filaments, there are some evidence from some electron microscopy that suggests that we might not be too wrong. Right? So the conclusion of this part is a very simple 0D model, very naive, can teach us a lot about actin dynamics, and it's because it's really well constrained by experimental data. Right? So there is another prediction that this model made is that the actin has a very fast turnover during this process. And so here what I mean by turnover is, if you go back to how the concentration of the protein changes over time, it's basically equal to what comes in minus what goes out, right? So to get this curve, you have one simple way to get to this number here is to keep adding stuff, so flux that is positive, and not remove anything, so flux that is 0 right here. So you keep adding stuff, and here you keep removing stuff, right? So at the end of the day, you're going to use the proteins only once. We're going to have here, like, let's say, 300 R2-free complex, right? But another way to get the same derivative here is to have this flux being positive and this one also being positive and being not 0, and the difference being the same, right? And if you do that, then you will use more proteins than the maximum you reach. And the model that actually fits this data predicts that 3-time turnover during the system. So why is it important? that there is turnover or not. It has pretty deep implications on the possible force production mechanisms. And remind you that we think that actin is doing something to deform the membrane, but we don't know what, and we don't know how. And here, knowing if it turns over or not will basically give us information about how the filaments can be organized and how they can work together to produce force. Right? But now the question is, how can we measure turnover? Right? As I told you earlier, it's a very fast process, and so using the classic methods of photo-bleaching recovery, the fluorescence recovery after photo-bleaching, called FRAP, is virtually impossible to use here because it's so fast and it's very small regions, and we're far from a steady state. So the strategy we were developing in the lab, it's a new single molecule strategy to measure the turnover, and the idea is to not measure the turnover the way FRAP would measure it, but measure the residence times of proteins in the system. Right? So the key here is to label proteins of interest. So with the GFP, we're labeling all the proteins of interest. And here the key is to label only one at a time in an endocytic structure. Right? So we use a snap tag with very low concentration of labels. We use a very high sensitive microscope to collect signals from single molecules. And we calculate residence times. Right? So it's a work in progress. So far, our data suggests that there is a little bit of turnover, but not as much as what the model predicted. But we're still working on it, and I encourage you to go see the posters from Mike Lacey over there. And also the poster from Gareth Dutz and Olivier Trottier. And that's going to be the quick commercial break for the Yale PhD program. So Gareth and Olivier, and Mike as well, but Gareth are from the PhD program, so PhD is for physics, engineering, and biology. And Gareth and Olivier were spent 3 weeks in my lab, and they worked together. So the idea is to pair physics students, Olivier, with the biology students, Gareth, and give them a project and let them work together and learn from each other how to do biology for Olivier or how to do some more computational analysis for Gareth. And they spent 3 weeks, and it's been even very productive for the lab itself, for us, and to move the project forward because it brought us also some new ideas for that. So they also have a poster over there. And by the way, most of the posters from Yale, actually from first-year students who did an integrated workshop, and it's basically 3 weeks of work. All right, that's the end of the commercial break. And I'm going to go very quickly on the second part of the talk. Now we want to know how the filaments are organized in the endocytic structure. One key question is the role of the filament cross-linkers, because from our quantitative data, we showed that the filaments are actually heavily cross-linked. I'm going to be quick. So just a quick reminder of filament cross-linkers. If you think about actin as stiff rods like that, the cross-linkers would bind on the side of the filaments and bind on basically grab two filaments and keep them together. And the question here is, are the filaments organized as a bundle, so all together like that, or is it a meshwork, right? And there's been some contradictory ideas and data on that what I showed with quantitative microscopy is that actually it's heavily crossing, but it's also the mesh size changes with time and basically compresses just before scission, right? So there is some interest. Also some preliminary data, and I'm going to be quick on that. The answer, the question here is, does it form bundles or meshwork? The answer is depends on mostly filament length and filament density. And we're working on basically understanding what's going on during hemoptytosis. And the even more striking result for us from the simulations is that if you add a tube in the middle of these randomly oriented filaments, you can even build a ring. And why not a contractile ring that could pinch off the tube, right? So another work in progress. And just to conclude, I want to finish with this slide on this quote from this statistician George Box, who said essentially all models are wrong, but some are useful. Completely agree with him, all models are wrong. But the question here is, how do you make the model useful? And so that's my tentative agenda for building useful models. And some people disagree with it, and I'm fine discussing it. So when I started grad school, I thought my job, when I had to build a model, was to develop the model and make it fit the data, right? What I realized during my postdoc and my first years of being a TI is that you have many more steps before and after, right? And so for me to make a useful model, you need to first start with a good biological question, and not first start with the model. Right? You need to identify a good biological question. Then you need to make sure that you have data available to test your model, and that the data you have, you're able to evaluate the quality of the data. Right? Then you identify the key variables and parameters, and here same story as with the model of the cow. You need to have enough details to make your point, but not too much to get lost in unknown parameters. But you cannot forget the important details, right? And you find the appropriate scale and granularity for your models. Then only at that time you find the right tools to make your model. Develop the model, you match the data, and then you need to go back and check that your initial assumptions are still valid and it still works, right? You need to do some kind of sensitivity analysis and explore the space of free parameters just to make sure that you don't have a particular case that is not relevant. You need to make testable predictions and then experimentally test them, right? I really love when model fails because that's when you really learn something is missing, and that's really where you can generate new hypotheses and go back and get some data and do another model, right? But to do that, you need to really understand well the biology and the biological questions, the methods, and the quality of data. Right? And that could be a full-time job, even if you remove number 6 here. Number 6 in itself can be a full-time job as well. Right? So with that, I want to thank people in my lab and people in my lab who are here. So there's Mike and Neil who are here, Gaël and Olivier who did the integrated workshop, and the PhD program for ATL and the Sackler Institute for existing and bringing students and TIs from different departments together. West Campus and American Cancer Society for seed funding, and iPoLS for bringing students from all across the world to talk to each other. So thank you.
Any questions for Julian?
So I consider this the influence of proteins, which I believe is very important, and proteins will influence your results qualitatively.
The influence of what?
The profiling proteins. So which way our influence will exchange rate between ATP active hormones and ATP active hormones.
Yeah, so that's on this slide almost. My point here is how important it is for the model, right? So for profiling, for example, or others, right? So you can include it in a parameter, right? That is, there's been some studies on that. The question is, where do you go into the details depending on what question you want to address, right? Here, the model I showed was broad enough and not detailed enough to have some predictive power, but also there's a lot of things where it fails. I mean, there's a lot of things where it fails for technical reasons, and there's things that I cannot capture with the model. And that's the reason why we're developing now a filament-based model like that, and that's just one step towards a more complex model, because there are a bunch of questions we cannot answer. But some questions we can answer without taking into account all the proteins.
I'm not sure if I understood this correctly. So you said that you had experimental data when you reduced your model to 0D, and you have to tweak these measure parameters to match the new experimental data. Can you comment on the degree you had to change these elements?
Yeah, so that was also on the last slide in some extent. Here the idea is to, let me go back to this one. Okay, so now you have this system of equations. Pretty much all the parameters here have been published in the literature. The thing is, we made some assumption here with, for example, the fact that let's look, for example, about this parameter here that we identified that we wanted to tweak. There are other ways to make the data fit, the model fit the data. The reason why we picked this one is because we knew from the literature, and when we did into the literature, that this one was the less accurately measured. And so what was published was actually wrong. And there's been, since we published the model, there's been other experimental data showing that it's actually, there's something wrong there, right, in the in vitro experiments that have been published before. Right? So the parameters we decided to tweak are the ones we were confident that they could be either mis-evaluated in the literature, or that the mechanisms were not so well understood, and so we had some freedom in some extent to propose new mechanisms. Right? So for the severing, for example.
So would you say that your model predicts the correct range of the parameter? The better experiment would reveal value that is closer to your fitted?
Yeah, so here I'm cheating a little bit by asking predictions on big words like that. The point was more to say, well, there is something, the model helped us to point out the things that were not right from the previous conception, or the parameters that could be wrong. And we gave some ideas that it will be faster. Happens that the direct measurements are not as extensive, the change is not as big as what we predicted, but we have other reasons to think that many factors will increase the...
Okay,